11.4, infinite geometric series. In an infinite geometric series, remember infinite means continuing without end to infinity. In this section, we will learn to find the sums of infinite geometric series. In an infinite geometric series, the sum is found by taking the first term and dividing it by 1 minus the rate. So the sum of an infinite geometric series is the first term divided by 1 minus the rate, provided that the absolute value of the rate is less than 1. If the absolute value of the rate is greater than 1 or equal to 1, then the series has no sum. Okay? So the series only has a sum if the absolute value of the rate is less than 1. Let's look at our first example. Looking at A in example 1, we notice that this series is written in summation notation, and we can see that it is a geometric series. Not only do they tell us in the directions, but if we're looking at it, we see that we have it in the form of the first term times the rate raised to, normally we say n minus 1 power, but here they're using the variable I to the I minus 1 power. So it's written in geometric form. So we have our first term and we have our rate. So, and remember, in infinite, and it goes to infinity, so this is an infinite series. In an infinite series, the sum is found by taking the first term and dividing it by 1 minus the rate. Well, the first term in this case is 2. Here's the first term. It's 1 minus the rate. The rate is the 0.1. Punch this into your calculator and simplify. And you'll find that the sum of this series will be 20 over 9. Let's look at the second one. Now they've told us in the directions that this is an infinite geometric series. What we need to know is what's the rate. We have the first term. Let's find the rate. Remember, to find the rate, you want to divide by the previous term. So 4/9 divided by 4/3, which would give us 12 over 36, which we reduce to 1/3. Could do the same thing, 4/3 divided by 4. You would still find the rate is 1/3, or 4 divided by 12. Still find that the rate is 1/3. So we have our rate, we have our first term, we can find the sum. The sum is equal to the first term, which is 12, divided by 1 minus the rate. Simplify. You end up with 12 divided by 2/3, or 18 as your final answer. The sum of this infinite geometric series would be 18. Let's go on to the next example. Alright, in this checkpoint, I'd like for you to pause the video and give this a try. Alright, hopefully you paused the video and gave it a try, and you should have found that this sum would be equal to a negative 20. If you had problems with that, go back to what the rule is. Remember, the rule is take the first term, which in this case was a negative 30. You should have found your rate. The rate here would have been a negative 1/2. So you want 1 minus that negative 1/2. Simplify it, you should have found a negative 20 to be the sum. Alright, let's look at example 2. In example 2, we're told it's an infinite geometric series, so we know the rule we need to use is that the sum would be equal to the first term divided by 1 minus the rate. we're given the first term, we're given the sum, we're asked to find the common ratio. So we're going to take the sum, set it equal to our first term, divided by 1 minus the rate. Now, this is set up like a proportion problem. One way to solve a proportion problem is by cross multiplying. So you want to take the 27 and multiply it times the 1 minus r, and that would be equal to the 5 times 5. So we end up with 27 minus 27r would be equal to 25. Subtract 27 from both sides, we have negative 27r would be equal to a negative 2. So therefore our rate would be 2 over 27. Alright, on the next slide, I'll give you one to practice. Pause the video, practice, then unpause the video and check your answer. Alright, hopefully you paused the video and gave it a try. You should have found that the rate, if that's what they asked you to find, the common ratio was 1/3. Alright, let's go on to example 3. Alright, something new. In example 3, we have the decimal, repeating decimal, 0.666666, and we want to write this as a fraction. Now, you already should know 0.66666 repeating as a fraction is 2/3. I'm going to show you how you can figure that out on ones where you would not know. Okay, so keep in mind, we already know that 0.66666 repeating is 2/3, but let's look at how we can find that answer so that we can do this for ones where we are not familiar with. One way to do this is to rewrite this decimal as an infinite geometric series. So we could rewrite it as 0.6 plus 0.06 plus 0.006 plus 0.0006. You can see what I'm doing is expanding this decimal answer, and this would go on infinitely. Okay. Now I'm going to come back and try to write this as a series. I want to know what my first term is, and try to write the rule. What would be the common ratio here? Well, to get your common ratio, okay, remember you take the we divide by the previous term, so we would want to take this 0.0006 and divide it by the 0.006. And when we do, we find that the rate, the common ratio here, is 0.1. Okay, so remember, then the rule can be written as the first term, which is 0.6, times the rate, which is 0.1, raised to the power of n minus 1. Okay, and we would be doing the summation of this. Okay, so that would give us our first term, second term, third term, fourth term. Now we want the summation of this infinite series. So it would be our first term, which is 0.6, divided by 1 minus the rate. We found our rate was 0.1. So we find that when we simplify this, 0.6 over 0.9, this gives us the fraction 6/9, which reduces to 2/3. Alright, let's look at the next one. Notice, before we go on to the next slide though, that when we only had one digit repeating, 6666, it was just one digit repeating, that the rate was 0.1. Hopefully we'll notice a pattern here. Let's go on to the next one. Alright, here's another example. This time we have 0.27 repeating. 0.27, 27, 27. So first let's expand it so we can see the pattern. So 0.27 plus 0.0027 plus this time I would need 4 zeros before the 27, and so on. So we're writing this as a series, the sequence here. Now let's come back and figure out what our rate would be. Remember, to get the rate, take and divide by the previous term. So take your last term, divide it by the previous term, and what you'll find is that the rate this time is 0.01. Notice that when we had two digits that are repeating, that the rate is 0.01, two numbers behind the decimal. So now that we know our rate and we know our first term, we can use what we know about infinite series. Take the first term, divide it by 1 minus the rate. So what we want is 0.27 divided by 1 minus the 0.01. And when we do that, we're going to come out with 0.27 over 0.99, or 27 over 99. Okay, slide both decimals over two places. We end up with 27 over 99. And then 27 over 99, don't forget to reduce. This will reduce. I should not have boxed that answer. The final answer you want to reduce always, and the final answer would be 3 over 11. Don't forget to reduce. Alright, let's try this a couple more times. This should get faster each time. Alright, a little bit different for this one. A little bit different. On this one, again, let's think about expanding. So this time we would have the 0.041. We need to remove the part that's not repeating. Okay, so separate that. Now, because I had two digits behind the decimal, I've got to have 2 zeros for that 0.41, and then before I get to my first digit that was repeating. So then I have to, for the next one, slide out 3 digits, 0.0006, and then so on. Now it's just 6 is repeating, so 0, need 4 zeros this time, and then a 6, and then dot, dot, dot. It will continue in this pattern. Okay, so a little bit different here. This time, what I have is this 0.41 is not part of the infinite series. It's the 0.41 plus the infinite series. Okay, so then the infinite series plus the sum of the infinite series here would be my first term of 0.006 over, we'd use our rule here. Now, there was only one digit that was repeating. Since there was only one digit that was repeating, it would be the rate here would be 0.1. So here would be 1 minus the 0.1. Okay. And so we would end up with 0.41 plus 0.006 over 0.9. Okay, now rewrite these as fractions. You would have 41 over 100 plus, slide that decimal over 3 places in the numerator. You'll slide it over 3 places in the denominator, so it would be over 900. Well, to add these, you've got to have a common denominator. So common denominator would be 900 to bring the work up here. Right, common denominator is 900, so the new numerator would be 369 over 900 plus 6 over 900. We would end up with 375 over 900, which then would reduce to 5 over 12. So 0.4166666666 repeating would be 5/12 as a fraction. Alright, how about you try it a couple of times? Right, 0.0272727 as a fraction. Pause the video, give it a try. Alright, if you did this correctly, you should have ended up with 3 over 110. Alright, try another one, just a little bit different. This one, you got 0.596596, repeating. Pause the video, give it a try. Alright, if you paused the video and gave it a try, you should have found that it would be equal to 596 over 999. 596 over 999. Okay, there was one more I should have put into the video. I forgot to put a slide in for it. I'm going to add it here. I'd like for you to now try to write this as a repeating. Take this repeating decimal, which is 6.05656 repeating. So 565656 repeating. Give it a try. Pause the video, give it a try, see what you can come up with. Alright, if you did it correctly, you should have come out with 2,998 over 495. This is what this would have been as a fraction. The work you should have set up would have been the 6.0 plus the infinite sum of 0.056 over 1 minus the rate of 0.01. Okay? If you have questions about that, you could see me tomorrow. Alright, let's try a word problem. Alright, let's look at the word problem. A pendulum swings 10 feet going left to right. On its swing back, it swings 90% as far as the first swing. Each successive swing is 90% of its previous swing. Let's look at part A. We want to find the total distance traveled by the pendulum when it finally stops. This would be an infinite sum. So what we need to know is, what is the first term? The first term is 10 feet. And then the rate. The rate is 90%, or 0.9 as a decimal. Remember, for an infinite sum, it'd be the first term, which is 10, divided by 1 minus the rate, or 1 minus 0.9. So when the pendulum finally stops, it would have traveled 100 feet. Alright, let's look at part B. When will the pendulum have traveled 50% of its total distance? So we want to know, when will the rate be 50%? Sorry, not when the rate would be 50%, but when we would have reached 50% of the total distance. Well, the total distance was 100, so we want 50% of that 100 feet. And we want to know when the sum will reach a specific number. So this is not an infinite sum, this is now a finite sum. So we want to use the rule for a finite sum. Well, remember, the rule for a finite sum in a geometric sum is that it's the first term. In this case, the first term is still 10, times 1 minus the rate, which is 0.9, raised to the power of the number of times, well, that's what we want to know, when, on what swing, over 1 minus the rate. And then solve. So 50% of 100 would be 50. Would be equal to 10 times 1 minus the 9 raised to the power of n over 1 minus the 0.9 would be 0.1. Go ahead and get rid of the 10 by dividing both sides by 10, which would leave you with 5 is equal to 1 minus the 0.9 raised to the n power over 0.1. Get rid of the 0.1 by multiplying both sides by 0.1. 5 times 0.1 would give you 0.5. Subtract 1 from both sides. So you would end up with a negative 0.5, but we want to get rid of this negative here also, so let's just write it this way. Move the negative 0.9 into this side. Equal to, subtract 0.5, so 1 minus 0.5 would give you 0.5. Alright, now remember to get rid of the base 9. Base 0.9, we'll use a log on both sides, so that on the left-hand side we're left with just n, and then it will be equal to log with a base of 0.9, log base 0.9 of 0.5. Punch that into your calculator. You're going to get 6.57888. Okay, so approximately 6.5 swings, or it asked us after which swing, so it would be after, we could say 6.5 swings or after the 7th swing. The final answer for part B would be after the 7th swing. Alright. I think that's a good place for us to stop. Just for some extra practice, you may want to try this SAT type question to see, how well are you understanding the material. Pause the video, give it a try, unpause the video, and check your answer. If you looked at it correctly, you should have found that A was the correct answer. I've done something a little bit different in this video. I've also included the homework answers, so that if you watch the video, you can check your homework answers, but remember, no work, no credit, so if you don't show any work, you won't receive any credit, but I thought it might help us save some time in class. If you were to check your answers before coming to class, then you can just come to class with any questions that you might have. So here you are. Here's 14 to 24. You might want to check these answers. Number 14, you should have said yes, and then the absolute value of the rate was equal to 1/5, and 1/5 is less than 1. 16, no, because the rate, absolute value of the rate was 4/3. 4/3 is greater than 1. Remember, the rate was supposed to be less than 1 for there to be a sum. 18, the sum is 9. 20 would not have a sum. 22, the sum is 10/9. And 24, the sum is 7. Let's check the next set. In the next set of homework answers, 34, you should have 23 over 25. 36 is negative 2/11. 38, you should have 4/9. Number 40, you should have 1. Number 42, you should have 23 over 99. 44, you should have 700 over 11. 46, 11,000 over 37. Make sure you're showing your work. And then the last couple of homework problems, you have a graph of an ellipse. 66, you should have written the rule -10 plus 8n. And 68, -5 times 2 to the n minus 1 power. All right, see you tomorrow. Come in with your homework questions, and we'll spend time going over your homework.